For today's algorithm, we're going to be discussing binary search tree search and insertion. But before we get there, let's quickly recap what the binary search tree property is. The binary search tree property states that for every node, the right subtree of that node must contain nodes that are greater than our current node, and the left subtree of that node must contain only nodes that are smaller than our current node. So we're going to use this binary search tree property in order to figure out how we want to search a binary search tree. So the intuition is pretty much that we're going to look at the current node that we have inside of our algorithm, and we're going to decide whether or not our key is larger or greater than that, or smaller than that node. If it is smaller, we're going to move left, and if it is greater, we're going to move right. Once we've reached our key, we're going to return it. So let's take a look at the actual algorithm. So our algorithm takes two parameters. It's going to take the key, k, and it's going to take the root, v. So the first part of the algorithm is it's going to check whether or not the root that we're currently at is null, or if the root that we're currently at contains the key we're looking for. If that's the case, we're going to return that root. So again, if it's null, it will return null, and if it's the node containing the key, it will return that node. Okay, on the flip side, if that's not the case, we're now going to compare the data with the key. If the data inside of the node is larger than the key, we want to move left. So we're going to return the recursive call of binary search tree search on the same key and on v.left. Now, if the data is greater, we're going to return the binary search tree search recursive call on the same key, but on v.right. So that's everything to consider for a search. Now the last thing to consider is runtime analysis of this. So there's two cases, two ways to look at the runtime here. First is the worst case. So in the worst case, the runtime of this algorithm is linear, or O of n. Because in the case that the tree is just a linked list, basically that every node is inserted either to the right or either to the left, we have to traverse every node potentially to reach the key we're searching for. On the other hand, in the average case where the tree is balanced, or the nodes are evenly distributed between the left and right children, the runtime is logarithmic, or O of log n. So let's do a few examples now. Let's consider this tree you see on the right. Let's search for the node with the key value 35. Well, we're going to start at the root, 50, and we're going to compare 35 with 50. 35 is less than 50, so we're going to move leftwards to 20. Now, 35 is greater than 20, so we're going to move rightwards to 30. Now, 35 is greater than 30, so we're going to move rightwards to 35. Now, since now we hit the base case of our recursive algorithm, since our key we're searching for, which is 35, is equal to the data inside of our current v, which is 35. Therefore, we're going to return v, and we return the node containing 35. Let's do another example, but this time non-internal. Let's search for 80. So the first thing we're going to do is compare 80 with the root 50, and we notice that 80 is larger, so we move right. We're now going to compare 80 with the right child of 50, which is 60, and we're going to notice that 80 is larger, so we're going to move right again. Again, 80 is larger than 70, so we're going to move right. And here we find that the key value inside of this node is 80, which is the key we're searching for, so we're going to return this node. Let's do one more example. Let's search for 5. So 5 is less than 50, so we move left. 5 is less than 20, so we move left again. 5 is less than 10, so we move left. But we're now at null, so our v is null. But luckily, we have a condition here that says if v is null, just return v. So our algorithm returns null, which makes sense because 5 is not within the tree. So this leads us directly into insertion into a binary search tree, because insertion is going to use the same intuition as search. We're going to utilize the binary search tree property to find where that node should exist. So let's take a look at the algorithm. Our algorithm for insertion is going to take two parameters: a node to be inserted, we're going to call it V, and the root of the tree, since we have to insert from the root in order to preserve the binary search tree property in all cases. So first, if the root is null, we're simply going to replace the root with our node V. So that case is taken care of. However, if we're not currently at a null root, we're going to check the data inside of our node and check the data inside of the root. If the data inside of the node is less than the data inside of the root, then we're going to set the left child of our root to be the recursive call of insertion on the same node to insert V, but now on the root's left child. On the other hand, if the data is larger, then we're going to set the right child of our root to be the recursive call of binary search tree insertion on the same node to insert and the right child of our root. So let's discuss the runtime of this. Once again, the runtime is the same as it is for search. In the case that the tree is completely unbalanced, such that it's a linked list, either all nodes are right children or all nodes are left children, the runtime is linear, or O of n. And of course, the average runtime, if the tree is balanced, is O of log n, or logarithmic. So let's take an example. Let's consider the same tree as last time, but now let's insert 5, since we saw that it wasn't there last time. So let's begin with this algorithm. First, we're going to check, is the root null? Of course it's not. So we move to our next step. The data inside of our root that we want to insert, which is 5, is less than the data at 50. So we're going to move left to 20. Now that we're at 20, we're going to do the same thing. We're going to check, is 5 less than 20? It is. We'll move left. We're going to check once again, is 5 less than 10? It is. So we move left. And we're currently at null. So we're going to return 5. And now we're going to trace back the recursive calls of our algorithm. Since in the last recursive call, we set 10.left to 5, 10.left to the return of the recursive call, it's going to set 10's left child to be our node 5. And it's going to reset 20's left child to be 10. It's going to reset 50's left child to be 20. And we'll terminate all the recursive calls. Let's do another example. Let's insert 45. So 45 is less than 50, so we move left. 45 is greater than 20, so we're going to move right. 45 is greater than 30, so we're going to move right. 45 is greater than 35, so we're going to set 35's right child to be 45. And the recursive calls are now going to complete. So 35's right child is 45, 30's right child is 35, 20's right child is 30, and 50's left child is 20. Let's do one more insertion. Let's insert 90 this time. So we start at 50. And 90 is greater than 50, so we move right. We're going to move right here, which is going to bring us to 60. Next, we're going to move right again because 90 is greater than 60, so we're going to head to 70. 90 is also greater than 70, so we're going to move right again to 80. Now, since 90 is greater than 80, and 80 is a leaf, we're going to set 80's right child to 90. The recursive calls are now going to terminate, so 80's right child is going to be set to 90, 70's right child is going to be set to 80, 60's right child is going to be set to 70, 50's right child is going to be set to 60. So that wraps up the examples for binary search tree insertion. One note I want to make here is that we're not considering the case where a key already exists in the tree. Now, each algorithm for this can handle it in its own way according to the application that the tree is being used for. In Sharp CS, we generally tend to believe these trees are sets. So in our case, we will do nothing if the key already exists in the tree. Thanks for watching this video. If you want to learn more about binary search trees or anything related to computer science, make sure to subscribe down below, comment, leave a like, and show respect, and click the cards in the top left and the top right. One should be over there, one should be over there. So stay tuned for more CS stuff.